Okay, we're going to start chapter 12 here today. This is the last chapter in our book here in AP Statistics. We've been spending the last several chapters, really starting with chapter 8, on all of these different inference procedures, starting with confidence intervals, and then we've been shifting to significance test. And so we've actually looked at different inference procedures for means, for proportions, and then in the last chapter, more so for counts when we did the chi-square test statistic. What we're going to be exploring here in this chapter is we're going to be revisiting something that we did in chapter 3, which is where we studied what's called bivariate data. And this is essentially when we go back to thinking of scatter plots. We had spent some time looking at scatter plots, how to kind of interpret scatter plots, things like residuals. So this chapter is going to prove helpful in just kind of reviewing some of that information as well. Specifically, what we're interested in this section when we do like inference for a linear regression is we're trying to estimate what we think the slope of a least squares regression line would be if we had the entire population of data. So we often, when we talk about a population, there is a particular variable that we use to designate that parameter, and then there is a separate variable that we use to represent the sample. So with means, of course, we're familiar with mu and x bar, with proportions, p and p hat, and with standard deviation, the sigma and the s sub x. What we're going to be doing here when we're working with linear equations is we're going to be, our main focus is going to be right here in trying to estimate what the population slope is. And so we're going to be using the Greek letter of the alphabet here, beta, to represent if you had all the points that you gathered from the entire population for whatever your bivariate data is. Okay, if you were to calculate a least squares regression line with the entire population of all of those data points, whatever the slope is of that regression line, we would identify that as beta. But if you're only taking a sample and you don't have all of the points, then you calculate the regression line, the slope is just b. Okay, quick reminder here that when we interpret a slope, remember a slope is always a rate. Okay, it's rise over run. So our y is in top, our x is in the bottom. We always interpret it as for each 1 unit increase in our x variable, your y variable is either increasing or decreasing, depending on whether it's positive or negative, by whatever that value is, okay? Now, an alpha symbol is what we're using to represent the population y-intercept, if we had all the points in our scatter plot, and an A would be the sample y-intercept. If you were to look on your formula sheet, the very, very front of the formula sheet, this formula right here is given as our kind of our regression equation. I'm just drawing your attention to that because you can see they use a B for the slope, and then they use an A for your y-intercept. Okay, something else that we'll be using here pretty frequently in this chapter is we're going to be using an S to represent the sample standard deviation of the residuals. Okay, sample standard deviation of the residuals. I know it's been a while since we've talked about residuals, so we'll definitely be revisiting that idea. And then we're going to use this sigma symbol to represent the population standard deviation, again, of the residuals. Okay, just keep in mind that the interpretation for a residual is generally that the observed y values are typically varying from the population regression by, and then it would be whatever that standard deviation value is. When you do problem number 5 on the homework, it's going to ask you in the context of a problem to define what beta, alpha, and sigma all are. And this front part right here on the notes might be helpful for you in doing that. So let's just look at an example here just to kind of get the gist of what this means when we're trying to estimate what a population slope is. What we have here is all of these points in this scatter plot represent, this is talking about the Old Faithful geyser, okay? And that is a geyser that erupts frequently, okay? And so let's look at what our x and our y variables are representing here. It's looking like the x-axis is representing the duration of the eruption in minutes. So this is how long the geyser is erupting. And then our y-axis is the interval between eruptions. So this is also a time, but this represents like what the time frame is in between when these eruptions are taking place. So again, if you were just to kind of picture here, each of these points, x is the duration, y is the interval in between these eruptions. And so they're paired up as a point here. Okay, now what we're going to assume we're looking at here in this scatter plot is these are all the data points paired up for the entire month. So for the month, there were 222 eruptions, and this represents the population for that month. These are all of the eruptions paired up with the interval in between the next eruption here. So you can see that over here in this box, we have our regression line that's drawn. Okay, the regression line is this faint line that you're seeing run through here. Remember, those regression lines are trying to run through the middle so that when you have some points that are above the line, you have some points distance below the line. Those blue segments I just sketched there represent the residuals. How far off the prediction, the line is the prediction, is from the actual observation. That's what the point is. Okay, so you can see here we have this predicted interval here. This is our y-intercept, this is our slope, and our x variable is the duration. Instead of an x, they just wrote the word duration. But I want you to focus on this 10.36. The 10.36 is beta. That is the true slope of this population regression line, because these are all the points representing all the 222 eruptions. Okay, so we know what the true population slope is for this. Okay. Now underneath here, you can see that these three graphs below, these three graphs represent three different simple random samples of size 20 that were taken from that population scatter plot up above. So essentially, we were randomly selecting 20 points from these 222 points, and we created, we did that 3 different times to get these 3 different graphs that you see below here. Okay, and you can see in each of those graphs a least squares regression line for that particular sample of 20 eruptions was created. And what I want you to notice underneath each of those here, you can see that what the slope is for each of these 3 regression lines. Okay, and notice that the slopes for each of these sample regression lines, negative 10.2, 7.7, and 9.5, it seems like they kind of vary quite a bit from what we know to be the true population slope for the regression line. It was 10.36 in the picture up above. Okay, so here's kind of the idea in this particular chapter. If there really truly is a linear relationship between x and y, duration and interval, if there really is a linear relationship in this population, is there one, or could the pattern that we're seeing in these scatter plots, because it definitely feels like there's this like positive association, all these lines are kind of slanted in a positive direction, or is it just possible that what we're seeing in these scatter plots is just happening by sheer chance from, the 20 points that we randomly chose from the population? Okay. Now, if there really is, in fact, a positive association, and I'm getting that because all of these lines are slanted in a positive direction, okay, then what that means is that beta is greater than 0. And it's greater than 0 because, remember, this is your slope. Okay, greater than 0 means that the slope is actually positive. Okay. So the pattern of variation in the slope that you're seeing for your sample slopes, that's what we're going to use to describe the sampling distribution here. Okay, so I want to just flip to the next page. Okay, oftentimes when we did this with means, we did this with proportions, we used a sampling distribution to help us kind of hone in on where the true mean, the mu was, or the true population proportion P is. We're going to do that same thing with these sample slopes of regression lines. Okay, so what what I want you to kind of think through here, and I'm just going to draw, you don't have to draw this, but we had used, this idea of if you were to, gather samples and calculate their sample means and do this enough, the shape is approximately normal, and the center of that sampling distribution is where you could expect the mu value to be located. Okay, and then we had a formula here for the standard deviation of that sampling distribution. How do you got the spread? Okay, and that was generally this formula, okay, which we often called the standard error of x bar. Okay, we did that exact same thing with p hats. We would use sample proportions to try to hone in on where the location really is of the true proportion value. Okay, and so we would do that enough. We would say the shape's approximately normal, and we would expect roughly in the center there to find the true value of p. Again, the spread of that sampling distribution we found by using, again, this is a formula on the formula sheet here. Okay, called that the standard error of p hat when we replaced the p's here with p hats. Okay, well, what you see pictured up here, just picture that all of these dots right here are really b's. Okay, so for example, I'm going to draw out samples like we did in size 20 points, say, from the population scatter plot. And each of those smaller scatter plots, I would run a regression line, and I would calculate the sample slope from that regression line, hoping that the center is going to land at what the population slope is. Okay, now there is a special formula for how to get the spread of this sampling distribution for the sample slope here. Okay, now this formula is a little bit different. It'll be on the next page, so you don't have to write this down. Okay, but this is the formula. We'll dissect that in a moment for the spread. But what I want you to just kind of get from up above here is roughly the shape is going to be close to normal if you draw enough samples here. Again, the center, we're going to expect the center to land spot on with where the true slope of that population regression line is. And you kind of, if you look at this, you can see that, right here they drew a red line where the center is. They're trying to say that that's pretty close to 10.36. And then the spread for this sampling distribution is 1.31. And we'll talk later about how to get that. And that has something to do with this formula right here that I just kind of jotted down there. Okay, let's go ahead and flip to the next page here. Okay. Okay, now, if you don't have census data, that means you don't have the entire population here to work with, okay, and all that you have is just merely a sample. Eventually, we're going to learn how to run what's called a linear regression t-test for slope. And what that test is going to reveal to us is whether we have enough evidence to try to conclude that there is a positive association with the slope. Okay? Positive association means that the slope is positive, therefore, as your x variable is increasing, the y variable is also increasing. Okay, now how that's going to look in terms of your null and alternative hypothesis, it's kind of got it written out, two different ways. One sort of in words, what it means, and the other using the beta symbol. But when we say that the population slope equals 0, remember our null hypothesis, always a statement of equality. If you think about how a line looks, if the slope is 0, it just is a flat horizontal line. There's no tilt to it at all, indicating that as x is increasing, y isn't doing anything. It's not decreasing, it's not increasing, it's just flat. So that is equivalent to saying that there is no association at all between the two variables x and y. Okay, as opposed to if our alternative hypothesis is trying to suggest that there would be a positive association between x and y, now we're talking about the slope would have a positive value. Okay, and so we would say beta is greater than 0 as our alternative hypothesis option here. Okay. Now, once again, if the data represents a census, then the relationship that you are seeing in your scatter plot, that's That's the true relationship. But oftentimes we don't have that population scatter plot, and instead what we have to look at is just a sample scatter plot. And so that then brings into question here, the question is whether the relationship that we're seeing in the sample is giving us significant evidence of the relationship between X and Y that exists in the population or not. Because sometimes what you're seeing in the sample is really just a very weak relationship between X and Y. And it might just mean that the population really doesn't have any association at all between the two variables. And so what you're seeing in the sample is just because of random chance variation in the points that you happen to randomly have selected from the population, okay? So it's a really important question to ask, is the evidence that we're seeing strong enough to show that there truly, truly is some type of relationship or association between X and Y values? Okay, so that brings us to anytime we describe a distribution, okay, a distribution, we are always needing to describe three things. We're needing to describe the shape, okay? The hope here is that we can say that the shape is approximately normal. There are going to be some conditions that are going to apply here. We always want to say what the center is. Of course, we just said that if you make a sampling distribution of B's, the center of that should be where beta is located. And then the spread, and here's that formula that I had jotted down earlier, the spread of your sampling distribution is denoted this way, okay? And notice the numerator is the standard deviation of the residuals. I'll walk you through how to do that here. And in the denominator, we're taking the standard deviation of the x coordinates multiplied by the square root of your sample, okay? Now, in order for you to state the shape, the center, and the spread of your sampling distribution for your slopes, there are certain conditions that you have to first show that you have met. So I'm going to walk you through, this is a pretty long list of conditions. I'm going to walk you through this list of conditions, and then we're going to just kind of fill in some blanks and apply it to an example on the following page. But this page here as well, I have an example just to kind of talk through. And as you can probably anticipate, AP Stats loves acronyms to help us try to remember our checklist of various things that we have to do. And so here are our conditions for saying the center, shape, and spread for the sampling distribution here for slopes. We're going to use the acronym LINER. Okay, notice this is not the word linear, there's not an A in here, but LINER. And I'm just going to talk you through these 5 aspects here. And as we touch on each one, I think I'll address it down here in this example at the bottom so that you can see what it looks like. Now, I don't want you to get too worried about, that you're forgetting how to make a scatter plot or a residual plot, rather. I'll walk you through that in the next video when we get into doing an example kind of from scratch here. Right now, I just want to walk you through each of these 5 conditions and kind of already have these graphs displayed for you. Okay, so the first condition is you have to show that your original scatter plot for your sample is linear. Now, you can do this one of 2 ways, but my preference is to show that the residual plot is showing you that the original scatter plot is linear. You could comment and say that the scatter plot that you're given appears to be approximately linear, but we learned back in chapter 3 that sometimes the scatter plot can look linear, but then when you make a residual plot, it shows a pattern in the residual plot, which means the original scatter plot wasn't linear. I think we talked how if you have a parabola, and if your scatter plot is just enough sections of the parabola that it might appear to be somewhat linear, when in fact there's a curve there that might not be notable to the naked eye, but when you perform a residual plot, it can sort of detect that there is a little bit of a curve happening there. The other reason that I'm going to suggest that you make a residual plot anyhow is because another aspect of checking these conditions is going to need you to make a residual plot anyways. Okay, so let's look at this example down here with the L for linear. you can see in both of these graphs, these two graphs here, both represent residual plots. And the one pictured on the left is passing this check because as you look at a residual plot, here's what you're looking for. You want to make sure that there is no evident pattern. Okay? If there's no evident pattern in the residual plot, then that means that it is approximately linear. Now, the "it" that I just said there was referring to the original scatter plot would be approximately linear if the residual plot shows no evident pattern. Now, if you look over here, you can see, oh, there's definitely a pattern in the residual plot. So that's why this one is failing this linear check, and because there is a pattern, we would have to conclude that the original scatter plot was not approximately linear. Okay, so that's the first check. The second check is something that you guys are familiar with. The I stands for independence, which we know we get our independence by doing the 10% condition. Now, you only do the 10% condition, though, if you have drawn a sample. If the problem is referencing an experiment, then we are assuming that we're achieving independence through the random assignment process anyhow, and you would not have to address this piece at all. Okay, so you can see down here, the independence condition, that's just 10% condition, or if it's an experiment, then we can just skip that condition. Okay. All right, the next one is normality. Okay, now, for the normality, what you would do, and again, don't worry about how to do this just yet. I'll refresh your memory on how to make a plot of the residuals. This is not the same thing as a residual plot. You would want to take all the values of your residuals, either make a probability plot, or I tend to gravitate to making a histogram of your residual values. And what you need to state is you would need to state that there is no major skewness or extreme values in your residual, or in the histogram of your residuals. Now, in this particular example down here for normality, you can see that this is kind of like a histogram. I guess they made it into a dot plot here. But you can see that in this particular dot plot, it feels like the shape is approximately normal, okay, symmetrical here. But here we can see that it's skewed. So this one definitely passes the check. This one over here fails the check, okay? And we would just want to make some remark that, you know, the plot, or maybe I'll say histogram of residuals, okay, the histogram of the residuals shows no major skewness or outliers. Okay. Okay, so back up to the top here, the fourth condition. The fourth condition is called equal variance. This is the E. And again, you would be looking at your residual plot. And here's what you're looking for. You want to look at the vertical spread of your residuals and make sure that it feels like it's roughly the same for the smallest values of X as it is for the largest values of X. Now, I'm going to scroll down here and show you what I mean by this here. This is called equal variance or equal standard deviation. Now, just to make sure it's clear what we're looking at here, I have kind of two examples. On the left, this is, on the top, you're seeing the scatter plot. At the bottom, this is the residual plot, okay? Now, I'm going to mark this over here. Here's another scatter plot, different set of data. Down here is the residual plot. I'm going to look at this residual plot on the right side. Do you see how over here are my smaller values of X, over here are the larger values of X? This is failing the check because it feels like the variance is very small for small values of X. Like my residuals are pretty close to where my regression line is because they're not very far off of this residual value of 0. But as I start getting to these larger values of x, see how it's starting to really extend way out and I'm getting much larger residual values. So this is kind of like this fans out. You can kind of see that fan happening. So I don't have the same variation for small values of x as I do for larger values of x. Whereas here, this feels pretty consistent. Okay, I'm not seeing that fan approach. You can kind of see the fan approach from the scatter plot by itself, but it's a little bit more apparent in looking at the residual plot there. Okay, so we would just simply want to say something like the residual plot shows that the variation is consistent across all the values of x. Okay, and then our last condition, the R in liner, is that random condition, which we're just either saying that a random sample was taken, or if it's an experiment, we would definitely want to mention that the treatments are randomly assigned. Okay, randomly assigned or a simple random sample was taken. So how you're going to start these problems is you're always going to start by making a residual plot with your data, and then you would also want to make a histogram of the residuals, okay, or a normal probability plot of the residuals, all of which we will review together. Okay, so all I want to do right now is just walk you through a quick example of kind of checking those conditions, and then I just want to briefly look at here before we look at those conditions, this formula for calculating the standard error of your sample slopes. Okay, so right here is the, kind of zoom in a little bit here. This is the standard error for your sample slopes. Okay, right here's the formula we're talking about. This formula is actually on your formula sheet, and I'm just going to show you where this is at on the formula sheet. You can see I pulled up this row here. If you look all the way to the right, see that S sub B? The top you have an S, the bottom you have an S sub x, and then it's square root of n minus 1. Okay, so again, the numerator represents the standard deviation of the residuals. The denominator, S sub x, is the standard deviation of the x coordinates. Okay, how we interpret this standard error for your slope is all standard errors, all standard deviations are really, showing how something typically varies from the population version of that. So this is estimating how much the slope of your sample regression line typically varies from the slope of the population regression line if you were to kind of repeat this process many, many times. Okay, so we're going to spend more time on that. Let's just look at this last example, and we will wrap this up here with looking at taking 10 helicopters and dropping 10 helicopters at each 10 helicopters were each, I guess, randomly assigned to be dropped. This is like a paper helicopter that you would drop at 5 different drop heights. So we're really working with 50 like paper helicopters, and we randomly assign 10 to 5 different drop heights. You can see here are the 5 different drop heights, and there are 10 dots above each one here. And what they're measuring is they are measuring how long the flight time is. How long is it staying in the air in seconds before it hits the ground? So our 2 variables here are the x, the drop height, and the predicted y variable here, the flight time. So I just want to label what these things are that we're looking at up above. This right here is a sample scatter plot. Okay, this is the original scatter plot. Over here, okay, this is the residual plot already made for you. Okay, down here, a couple different things. This is a histogram, not of the original data. This is a histogram of the residuals. Okay, and what you see over here is a normal probability plot of the residuals. Okay, now just to expedite this, I kind of filled in, or I guess constructed this in such a way that we can just kind of fill in the blanks to sort of check off all 5 of these conditions for liner. Okay, so the L in liner represents making sure that that original scatter plot appeared that it was approximately normal, or if we look at the residual plot, that that's showing no evident pattern. So I'm looking at this, yeah, this kind of feels like this is, showing approximately linear form. Also here, I'm not really seeing a definitive pattern here. Again, my preference is to use this, but you could say the scatter plot shows an approximate linear form, or the residual plot shows no evident pattern. Okay, either one of those two statements would check off the linear condition. Okay, keep in mind this felt like this was an experiment. Remember they said they were randomly assigning 10 helicopters each to these 5 drop heights. So I really don't have to address this. I'm just going to say that this condition is met because of random assignment. Okay, this was an experiment, so we don't really have to do the 10% condition. Okay, the normality condition is met by you either looking at the histogram of the residuals or a normal probability plot of the residuals. If you're looking at the histogram of the residuals, you would want to be looking to make sure that it is approximately normal. Okay, definitely feels like that's the shape here, with no extreme skewness or outliers. Okay, that seems pretty good. Or if you're looking at the normal probability plot of your residuals, you would want that to appear that it was approximately linear. Okay, approximately linear. And we were definitely kind of getting that by looking at this and seeing that that was approximately linear here. Okay, E. Okay, this is that equal variance piece. You want to go back and look at your residual plot, and you're checking for if it's fanning out. Okay, it might feel like it's getting a little bit bigger here and there, but then it comes back down again. So there's no evident like major either fanning that way or like fanning this way. So I'm going to say the residual plot shows similar amounts of vertical scatter for all values of x, small and large values of x. And then finally, the helicopters were randomly assigned to their drop heights. So that meets the random condition. Okay, we will pick up here on the next video. Just a couple problems for you to go ahead and try here.